the second part of the lecture I want to go on mixed mode, and after that I start to introduce a bit notches and three-dimensional effects, as I mentioned before. But actually, I think one of the most critical problems that we have when we have a fractal mechanics problem is that usually it's very difficult to have a component subject only to mode 1. And so usually you have a configuration where you have a kind of mixed mode loading combinations. So you have cracks that are inclined with respect to the direction of the load. And so actually the local mode 1, the local stress field is not mode 1, but is a combination between usually mode 1 and mode 2. And if you have also out of plane loading, it's a combination also with mode 3. So actually the problem of how to treat these modes in terms of final fractal prediction was studied many years ago. And the first two to study the work were George C. and Fazil Erdogan in the group of Lehigh University that I have shown to you before. And they start to make some experimental tests with the inclined cracks to understand how they behave and how it is possible to predict the behavior of these cracks when they are failing. Actually, the first paper that was produced from this study was dated 1963. It's a very famous paper that has nowadays more than 2,000 citations, and it's always referred as the most important contribution for mixed mode loading. Actually, it was establishing a criterion that is called maximum tangential stress criterion. It is based on the idea, so the maximum tensile stress criterion, or MTS criterion, is based on the idea that if you have a crack subject to mixed mode loading, the direction of the crack propagation is the direction where locally you have a mode 2 that is equal to 0. So locally the crack tends to propagate in the direction normal to the local stress field, so in a condition where you have a kind of equivalent mode 1 condition. And so actually what George C. and Erdogan find out is that you have this kind of relationship that the crack tends to propagate when this equation is solved. So actually when the contribution of the stress due to mode 2 in this direction is equal to 0, and when actually locally you have a kind of point or a kind of cube of material that is only subject to tensile loading locally. So locally there is not mode 2, and so the criterion is also closed. It is also called the local mode 1 criterion. Actually, it's very simple because it's a kind of imposition that locally you only maintain mode 1. After that, George C. also improved the method, introducing a strain energy density approach that has two advantages. It's also sensitive to the Poisson's ratio variation, and is also sensitive to the mesh. Is also insensitive to the mesh size. So this is a big advantage. But actually, in terms of angles of prediction of crack propagation, is very similar to the maximum stress criterion. So there is not a big difference in terms of angle prediction with respect to the maximum stress criterion and the strain energy density criterion. Actually, they give almost the same value of angle in terms of crack propagation. This table is reported in a book that is nowadays used for teaching, that is Sung Ing book, that is called Fractal Mechanics and published in 2012 from Taylor and Francis. What it is very important when we deal with fractal mechanics is that we are assuming a linear elastic behavior for our material. So what it is very important is that we always can use a superposition principle for solving a complex problem. So this is very important. Actually, if we have a combined case like this, so where we have a remote stress field and a point force applied here, we can always say that the complex model can be divided into sub-models. The first one is the one with the remote stress, and the second one is one with the punctual stress or punctual force applied here. And if you have the closed form solution for this and the closed form solution for the two sub-model, after that the combination of the stress intensity is the sum of the first term plus the second term. So the advantage of having a linear elastic model is the possibility to always use superposition principle. You don't have to repeat the model. Also, if you change the stress level of 2 times, the stress intensity factor increases 2 times. So you don't have to remake any kind of model. So the superposition and the scalability with respect to the load is a very important effect of using a linear elastic hypothesis in your modeling. But actually, locally, as I have shown before, plasticity occurs, and so what happens is that sometimes plastic field is not negligible, and we need to take into account of it. And so there are also elastic plastic fracture mechanics solution. But of course, when you introduce plasticity, you lose the possibility of overposition principle. So any time that you apply a load to your component and you obtain a solution, that solution is only valid for the applied load that you have applied to the elastic plastic solution. Actually, the integral is very flexible, can be applied also for elastic plastic solution, and actually the stress field for a crack in elastic plastic condition is based on a J integral definition, and is based mainly based on the work of John Hutchinson. As always happened in that period, there were different people working on the same topic. Rice and Rosengren obtained a solution, and Hutchinson obtained a solution in the same year, and after that they start to fight for which was the owner of the solution. But actually what it is very interesting is that you can express the stress field of the material according, generally in terms of J integral, and according to a kind of elastic plastic rules for your material that is not more linear but is following these rules, so is following a kind of potential rule where n is the hardening exponent of the potential expression of your material. You can also use a Rambert-Osgood equation for your material, but what you are obtaining is a stress field that is a function of J integral, a function of an angular function of theta that is still depending on n, and this is also the reason because the stress field is not scalable in terms of loading and in terms so the overposition principle is not valid because the angular function are also depending on the strain hardening material property. Okay, and after that you have this contribution in the exponent of n that is a material property parameter. So actually, if you consider a kind of estimation of the plastic radius, it's always very convenient to be able to estimate in some way which is the plastic radius of your material. So if you have a crack, you have always the possibility to understand which is the size close to the crack, that is where inside which the material is over the yielding strength of the material properties, and so you can measure the radius and you can define this radius as plastic radius of the material. If the plastic radius is very small, you can apply without any problem linear elastic fracture mechanics. If the size increase, probably you need to go through a more complex model considering elastic plastic mechanics solution. Of course, the shape of the plastic zone is depending on the mode that you are applying. If you have the plastic zone shape for mode 1, you have like this butterfly shape, but if you have mode 2, you have like a 8 shape, and if you have mode 3, it's perfectly a circular shape. Okay. So what Hutchinson made was to describe the elastic plastic stress field in small scale yielding, so the plastic zone is small with respect to the K field. So you can almost consider the first plaster of the stress field elastoplastic. But if you are interested to a zone that is larger, so if the process zone that you want to use for the design is larger, you can use linear elastic fractal mechanics. But if you are in the condition where you have a large plastic yielding, it means that the plastic stress field is larger, and so actually you have to design in this field, and you have a linear elastic fractal mechanics only outside that region, but is not interesting for the design process. So what it is important to know is in some way the size of the plastic radius for your material, and if you estimate that value according to the load that you have in place in the service condition of your components, you can decide if you are in small scale yielding, in large scale yielding, or if you are actually in fully linear elastic condition. This is very important for selecting the way in which you are presenting the material. Actually, if you consider this configuration, this is the stress field, n equal to 1 means a linear elastic trend of the material, and you have a slope that is 1 divided 2 of the stress field. If you increase n, so if you are going until, if you are selecting a material that have a hardening exponent equal to 3, the slope is decreasing, actually. And if you consider a kind of elastic plastic material, you have a fully plastic behavior, it means that n is equal to infinite, and actually you don't have any stress singularity, and the stress field is almost constant. So you are almost in the static case without any crack. I think it's interesting to mention that this approach was also extended to notches by this team from Padua, where Lazzarin was leading. Livieri, Zambardi and Zappalorto were also very active on this field, and they were able to actually define a stress intensity factor that is also a kind of plastic notch stress intensity factor that is a useful parameter to describe the stress field under under elastic plastic condition in presence also of V notch and also of cracks. Okay? And of course, the scale effect is also present for this kind of behavior. It's only the exponent of the stress field that is changing, so the scale effect is changing proportionally to the stress field slope. I promised to you before to arrive at least to the Williams-Asymptotie solution for under linear elastic conditions, and now we are here. Actually, considering closed form solution, this is the most important contribution dealing with V notches. And actually, as I said before, if you consider a notch, it's like an extension of the crack case. The only difference is that you don't have a parallel flank of your defect, but you are opening the face of the geometrical discontinuity, maintaining the notch radius equal to 0. So the crack is a special case of this V notch shape. Okay? And the first to solve the issue, we just mentioned that the first one was a German 10 years before, but the most famous contribution is due to Williams, that published Williams was a mathematician mainly, not interested to engineering problems at all, but he was interested to solve this issue, and he tried to understand which was the stress field close to the notch tip in presence of a radius equal to 0. And actually he used an iris stress function in a very simple shape that was a kind of contribution depending only on R, and a contribution only depending on theta. And what he did, it was to express f theta as a function with some constant, as an angular function of theta, and introducing A, B, C, and D that are constants that have to be determined under imposing some boundary conditions. Actually, actually the aim of William was to solve both the mode 1 solution and the mode 2 solution. So he places the blue terms that corresponds to the symmetric part, so the mode 1 solution, and the red part that are corresponding to the antisymmetric or shear stress solution corresponding to mode 2. Okay? And what he did, it was to apply the angular expression of the iris stress function, and by imposing the boundary condition on the edge of the notch that have to be traction free, so without, so if you want that the component, the boundary condition respect the radial stress has to be 0, and the tangential stress has to be 0, and the shear stress has to be 0 along the traction free edge of the notch. He imposed these 4 boundary conditions on both edges of the notch. So you have 4 conditions, and you are able to determine the 4 constants, and you are able to obtain the stress field close to the notch tip. Actually, the Williams asymptotic solution consider that the strain energy is small disk of radius rho around the corner. And actually, it is important to understand that this value, this consideration on energy is valid only if lambda is greater than 0, because if lambda is lower than 0, we have an infinite energy close to the notch tip, which is an impossible solution from a physical perspective. Actually, what he did, it was to impose that sigma theta and tau r theta are equal to 0 along the flanks of the notch, and imposing these boundary conditions that are quite simple from a mathematical point of view, he was able to find out these simple solutions, and actually he was able to show that there are 2 equations, one for mode 1, which is the symmetric part of the solution, and one for mode 2 that is antisymmetric part of the solution. Lambda, which is the unknown parameter in these equations, is called the eigenvalue of the solution, and is actually the degree of singularity of your stress field close to the crack tip. So if you consider lambda minus 1, and if you consider the crack tip, you have a slope that is minus 0.5. If you consider a notch, so if you are moving back in this graph, because you are considering a notch, 2 times alpha is the supplementary angle to the notch angle. So in this direction, you can open the angle, and the eigenvalue is decreasing according to this slope until you reach the condition where you have completely not a notch but a plane specimens without any geometrical discontinuity, that is this point. What it is interesting to understand is for symmetric case of mode 1, the stress field is singular from the crack case until a notch opening angle of 180 degrees. For the mode 2 condition, the stress field is singular, so tends to infinity at the notch tip from 0 until this angle. So actually there is a limitation, so there is a point where at a certain point of opening the angle, the mode 2 becomes not singular, and only mode 1 remains singular, which is very important consideration. Actually, as we made for the crack tip, it's possible to define the same definition of the stress intensity factor that it is in this case as an extension is called notch stress intensity factor. That is again a function of the stress field close to the notch tip, multiply the square root of 2 pi, multiply r with power 1 minus lambda 1 and 1 minus lambda 2 if you are considering mode 1 and mode 2. Of course, the slope of the stress field is given by 1 minus lambda 1. If we have the crack case, so a notch opening angle of 0, we have 1 minus lambda 1 that is equal to 0.5 according to linear elastic fracture mechanics. So actually, the crack case can be seen as a kind of simplified or special case solution of the Williams solution. And again, also in the case of a notch opening angle, what it is interesting is that we have a field parameter that is a constant value close to the notch tip. So we have K1 that is constant according as a function of R. what it is also interesting is that if you change the notch opening angle, K1 and K2 are changing their unit of measure. So if you have a different notch opening angle, you have different value of the unit of measure for K1 and K2. This means that if you have a different notch opening angle, you cannot directly compare the value of K1 for a notch opening angle, for example, of 120 and for a notch opening angle of 150 because it's changing the unit of measure. Okay? So this is also very important, and this is also a limitation of the approach, of course, because you have not a direct comparison between different notch opening angles. This is a very strong limitation. Of course, as I said before, the Williams solution is a special case of the Irwin solution is a special case of the Williams solution, and actually, what is it is interesting to show, and it was also discussed from Williams, is that it was also discussed from Irving before, is that what we are considering in linear fractal mechanics is usually the first term of a kind of series development. So when we are considering the stress intensity factor, also in Irving equation, we are only considering a part of the solution and not all the solution, because the solution has also higher order terms that are more complex and are changing the exponent here. And so the leading term is a function of the stress intensity factor, and for those terms the slope of the stress field is minus 0.5 for the crack field. But if you want also to consider more high order terms, and this is sometimes important for thin specimens, you have to develop the series considering also higher order terms. So it's also important to remember this. Actually, 95% of our applications are based on the main leading term, and we are automatically neglecting the higher order terms. But it's important to know that for thin components, sometimes the contribution of the higher order terms, and the first order terms is the T stress, that is sometimes very important, has to be taken into account. After that, Lazzarini and Tovo in 1996, restarting from historical works by Krieger and Paris and other works, were able to find out a fantastic, in my opinion, solution for generalized notch. So considering not only a notch opening angle, but also a notch tip radius different from zero. So they extend actually the Williams solution to a notch radius that has an opening angle of 2 times alpha, and the notch radius that is different from zero, giving a very, very interesting solution. They use the complex potential method, and they apply Muschelis-Willy-Kolosov that we didn't have the time to see today, but actually is not so far from Airy stress function method. What they did, it was to, of course, they put in the notch radius. This created a more complexity in the solution, so they got more constants to find with respect to Williams, but taking into account also the notch radius. But they were able to impose very, very smart boundary solutions in the PhD thesis of Roberto Tovo, and they were able to find out this final solution that has 2 parts. The first part actually is the Williams solution, and the second part is taking into account the notch radius contribution. So they are very useful because actually with this solution you can treat in a generalized way not only the Williams solution and the crack solution, but any kind of joint with any shape and any notch radius. So, of course, as a special case of this solution, you can see that we have a Williams solution, but Lazzarini and Tovo were able also to give, as a function of the notch opening angles, all the parameters necessary to apply very easily the equation in a closed form. So actually, also for a non-expert person in engineering fractal mechanics or notch mechanics, the applications are very easy to use and implement because there are these tables that are reporting the coefficient as a function of the notch opening angles, and they make the use very, very useful. And that, of course, they define the stress intensity factor in the case of a sharp notch, but they were also able to extend this definition to a kind of generalized notch stress intensity factor that is not only taking into account the sharp case, but is also considering a round notch. So they define the kind of stress intensity factor also in the presence of a notch radius different from 0, extending Gross and Mendelssohn definition of 1972. One of the most interesting applications of these results is the study of welded joints. Because actually welded joints usually face from the weld toe or the weld root in the case of lack of penetration. So usually the two critical points for a weld joints are the weld toe and the lack of penetration, which can be considered like a crack. Okay? So what Lazzarini and Tovo did was to apply their analytical frame to this case and to express the stress field for mode 1 and mode 2 as a function of the stress intensity factor. Of course, this equation, if rho is equal to 0, is also a kind of Williams equation in this case. And they verify the validity of the equation considering finite elements and different kind of notch radius and notch depth and notch opening angle, and actually the solutions are very accurate for different kind of configuration notch opening angles. I will go back later to the design of welded joints. The problem of the approach of notch stress intensity factor when you are designing a welded joint is that if you have a weld toe and the weld root, here you have a crack and here you have a notch which can be considered with an opening angle of 135 degrees, but as we have discussed before, the notch opening angle with 135 degrees has a different stress intensity factor or notch stress intensity factor, which has a unit of measure that is different from the unit of measure of the crack tip. And so if you don't know where the failure happens, here or here, you cannot directly compare the stress intensity factor because they have different unit of measure. So this is the limitation of a stress intensity factor approach or not stress intensity factor approach for welded joints. Usually, if the weldment is well designed, the failure is always happening at the weld toe. And so, actually, you can neglect the contribution of the weld root. And in that case, the not stress intensity factor is a very powerful parameter. But still, it has the limitation that is linked to a stress field distribution, so is mesh sensitive. You need a very accurate mesh close to the notch tip to evaluate accurately the stress field. And if you need a verified mesh, this makes the application, the computational application, very complex if you have a complex geometry. Okay? So, the first to try to solve the problem of a notch using a kind of very old approach based on iris stress function was Neuber in the book of 1937 when he was only 32 years old. So he wrote this book when he was only 32 years old. And actually he tried with this complex iris stress function equation. He was able to find out this stress field exponent as a function of Q. And after that, he was able to express only, because it was very complex, only the sigma theta along the notch bisector line using the definition in Cartesian coordinate of the iris stress function. He find out this solution. Actually, this value of t is not so different from the value of lambda that is present in the Williams solution. So this solution is not so far from the solution of Williams in terms of eigenvalue. What we did later in 2009 was to modify the solution by Neuber improving the solution, and actually we were able to obtain a very accurate exponent for the stress field, and also a stress field that was able to predict the stress field also at a far distance from the notch tip and using complex mode loading conditions. Actually, considering a comparison between finite element analysis and Neuber solution, you see that the Neuber solution is deviating from the finite elements, but what we did in 2009 with the contribution of myself and Radai was to improve the solution, making almost perfectly solution, changing as a function, for example, of the notch radius, you still maintain a very accurate solution. Of course, here it seems a very small difference, but it is 30–40% that can be very important for the final design of a component. It's not so small. So we exchanged a lot of fax because Radai was the old professor, so all the communication was made by fax. I want to also to remind a very funny episode that happens to me. He actually got a very old Mercedes with the fax inside the car and connect to the battery of the car. So we start to fight for a kind of coefficient during a trip that he made, and so actually I completely destroy his battery of the car, and after that he was completely upset with me because I sent many pages of analytical discussion and the points to him, and actually he was not able to reach the hotel during the trip, so it was quite fun. But we fight a lot for this paper, and because of course he's very German. Actually it was a very good collaboration, but it was very complicated because the topic was new, and we start to modify very well recognized equation by Neuber that was German and very famous there. So to change those equations, it was very difficult to publish the equation, and to make the paper accept engineering fractal mechanics takes 2 years of work, because also the reviewer were very upset about the solution and the improvement of the solution. So actually we made a lot of round of revision with a lot of improvements, and it was quite tough. What it is also interesting is that, and it is also a very important diagram in my opinion, is that if you consider the stress concentration factor Kt, as we have seen before, this stress concentration factor, if you want to use this for design purpose, actually the fatigue life or the strength of your component, also under static loading, is decreased by Kt following this line until you reach a certain value that is Kt star. If you make an experiment over this value of Kt, actually you don't follow this line, but you don't have any sensitivity to the Kt increase. This means that in this region Kt is not working for the design because it's too conservative. So actually Kt star is giving us the threshold between the actually traditional design based on a point method and this plateau value that is making us understand that Kt is not working. We need to leave Kt and the point approach and we need to go for a fractal mechanics approach, because actually the value of Kt is increasing too much. If we use this decrease of fatigue life or fractal life following Kt decrease, following Kt increasing, we are decreasing too much the fatigue properties of the material that is not following their rules. Okay, and actually this was also interpreted in another way by Smith, Watson, and Topper in 1979 that they gave us another important information both under static and under fatigue loading. This is the interpretation under fatigue loading. I think you have seen before the delta K threshold in the Paris curve that I have omitted in this presentation. But actually, as I said before, there is a value that is a kind of material parameter depending on the threshold value of the stress intensity factor and the fatigue limit of the uncracked material, that is called A0. If you are over A0, actually you are, so if in your material you have defects that are bigger than A0, you are decreasing the material, the component life according to this law. So you are following exactly linear elastic fractal mechanics. If in your material of your component you have defects that are lower than A0, the material is not sensitive to this defect, so almost you find out that the material behave like a kind of uncracked material, because the material is not sensitive to defects that are lower than A0. So A0 is called intrinsic crack length, so it's a kind of indication of which is the critical size of a defect for our material as a function of delta K threshold and the fatigue limit of the uncracked components. If we are below the threshold, we are in the case of actually uncracked material. Of course, nature is not making sharp transition, so the decrease is a kind of smooth transition like this. But the original diagram of Kitagawa was like this. Was a sharp connection. So A0 is giving us a threshold value. Here we are not sensitive to defect if we have defects lower than this, but here we are very sensitive to defect. And A0 of course is a function of the temperature. So if we have a lower temperature, A0 is decreasing a lot, and so actually defects that were not so important at room temperature become very, very dangerous at lower temperature. And this makes the design very complicated. And Lazzarin and Azzori in 2001 for the first time, and after that in 2005 with also Professor Meneghetti, they extend the Kitagawa diagram to make a kind of generalized diagram that in the first part is the diagram that we have seen before with linear elastic mechanics, but they add a second part that is the kind of contribution due to notch, and actually the diagram behave like this. In this second part, this part is the unnotched uncracked component, this part is the linear elastic fractal mechanics component, and this part is the notch component. So in one single diagram they were able to represent all the material, and after that they were able to use the scale factor for also taking care of the real component of the real size of your component. Actually, they apply the criterion to different materials, and they were able to summarize in a very, of course, different structural material in the same diagram, proving also the existence from an experimental point of view of the smooth transition of the diagram in this part. So after that, we also extend. This is a recent contribution. This was my paper published in 2007. We are able to extend J integral that was initially taught for the crack case also to a sharp notch, and after that to a blunt component. Of course, what is only changing is the complexity of the analytical frame, but the definition of J integral remains the same, and what we are losing, opening the notch opening angle, is the path independency, because if you open the notch, you are losing the property of path independency that is only valid for the crack case. We plot this analytically in a work published in 2007. It was more a mathematical work, but actually after that we give also some useful tool for design. And so if one wants to be fixed or want to use a J integral for design, you can find all the closed form expression also for blunt notches based on Lazzarin-Tovo solution in this paper. And actually we are able to predict the failure in blunt notches under 3-point bending under mode 1, considering different notch depth, considering different notch radius, and we are able to predict quite well the fracture behavior under static loading with this generalized J integral approach. What it is very interesting and not well known until now, this is still an open field of research, and actually me and Professor Lazzarin, Professor Cook and Professor Kotosov have worked together on this topic, is to study three-dimensional linear elastic fracture problems, and actually some recent results that are very interesting. As I said before, usually we consider plane stress and plane strain as a main hypothesis for using, for defining the stress intensity factor and mode of failure. So we have mode 1, mode 2, and mode 3. But if you consider a finite thickness, this is changing completely what is happening locally in your component, especially if you have a sharp component. Actually, what we did in the past was to start with a very, very simple component. We start like for making a kind of trial. We start with a very simple, also because we start during my master thesis, so it was 16 years ago, and the power, I started using ANSYS 3.0, now the version is probably 19 or something like this. So we almost use a very, very preliminary version of ANSYS with very few nodes. And so we start from a very simple solution. And actually we studied the effect of the finite thickness on the stress distribution. And what we find out is that if you consider the thickness effect along the thickness of the plate, if you consider a kind of hole, usually you expect a stress concentration factor equal to 3, but in the mid plane, yeah, you have almost 3, but you can have also 3.2, depending on the ratio between A, which is the radius of the notch, and H, which is the thickness of the plate. And also it's sensitive to the Poisson's ratio. In this graph is not reporting sensitivity with respect to the Poisson's ratio. So in the free surface you can have actually a lower value, and also on the mid plane you can have a higher value of the stress concentration factor. So actually also the well-established key solution is wrong or approximate if you are considering a finite thickness for your component. Of course, you are not making a big mistake, but still, if you have an A divided H ratio that is equal to 4, you have an increase of 20% of the stress concentration factor at the notch tip, which is not negligible. What it is very interesting is what is happening if you have a three-dimensional solution in cracked components. So an extension of linear elastic fracture mechanics to three-dimensional components. We have discussed all the day about two-dimensional solution for elasticity. We have introduced K1, which is the fracture parameter, K1C or KC, that is the fracture toughness. We have discussed plate stress and plate strain conditions. But what is happening if you consider a crack where you have a finite thickness of your component? So this is the open question that we try to answer. Is changing or not changing the stress field close to the crack tip? How is changing? Which is the most important contribution, mode 1, mode 2, or mode 3? There are other modes that are coupled with the primary modes, so we try to answer to this. And actually, the overall problem is very complicated because it requires, of course, a lot of computational effort for solving the problem numerically. And because when we started this, we didn't have many computational support or tools. What we tried to do was to study a very simple problem of a disk where we simply consider a finite thickness H, and after that we apply some boundary condition in terms of displacement around the disk, representing mode 1, mode 2, and mode 3 solution to find out what was happening locally to the crack tip when we apply poor mode 1, nominal poor mode 1, and nominal poor mode 2, and nominal poor mode 3. So what we find out is that under poor mode 1, it's like what happens with the circular hole under poor mode 1. You have a trend that is a stress field that is strongly changing along the thickness of the plate. So you have the maximum stress field in the mid plane of your component, and you have a decrease of the stress field when you are on the free surface. So of course this is half of the plate, and of course this is changing a lot if you are considering a small value of Poisson's ratio. So if you have a Poisson's ratio 0.1, so for example 0.1 is for some ceramic materials. If the sensitivity is very small, you have almost a straight line. If you have 0.3, you have a difference between the mode 1 solution, the two-dimensional mode solution, that is 7%. If you have a 0.5, that is very difficult to have. But if you are in a condition of a polymer that is, for example, 0.4, you have an increase of 15% or more in the terms of the stress intensity factor. So also here it's not negligible, and you have to consider this effect. But what it is very interesting is what is happening if you consider mode 2 stress field, which is the most interesting part. So actually, what we did, it was to apply a kind of nominal shear stress to our component, and due to the three-dimensional effect of the finite thickness, what you can find locally is that you can see also an out-of-plane displacement in this direction. Actually, you are applying mode 2, but what is happening is not only mode 2, which is this configuration, but due to the thickness or Poisson's effect, you are pushing in one direction, and you are putting tensile under other direction. So what is happening is that you have also a kind of Poisson's effect close to the free surface of the plate. So locally, what you are generating is a kind of coupled mode that is called mode O, and it is called out-of-plane mode of fracture that is not predicted by two-dimensional fracture mechanics solution. Okay? And actually, this KO, that is we call this stress intensity factor linked to the out-of-plane mode KO, is not negligible, because actually applying a remote stress intensity factor of mode 2 that was equal to this, close to the free surface of the knot of the crack, quindi close to the free surface of the plate, sorry, we have a value which is very close to the maximum value that we are applying nominally. So this effect is not negligible. Actually, this explains many failures that we have from the free surface of the components in a three-dimensional components that are not easy to explain if you consider b-dimensional models. So this was a very good scientific achievement. And what we did later was to make the same. So we apply, in this case, a nominal poor mode 3. And what we obtain is that the poor mode 3 is also transferring to the component a local mode 2. So actually, mode 2 and mode 3 are always coupled together and are generating some additional mode 2 and mode 3 locals that are locally present close to the free surface of the component. And also in this case, the value of the K3 local, the value of the K2 local was induced, the couplet mode was not negligible. So it was a very high intensity with respect to the generating mode. So actually, we made a lot of finite element results, but what it is interesting is that we were also able to prove the existence of this couplet mode by means of some experiments that we make at the University of Adelaide in 2011. And with the digital image correlation, we were able to find out the displacement. So we apply mixed mode. First we tried with mode 1, and after that we apply also different kind of combination of modes. But actually we were fine to detect the existence of an out-of-plane mode coupled with the nominal remote load applied to the component only locally on the free surface of the components. Actually we were quite lucky because the most important effects of three-dimensional effects are close to the surface. So it's possible to detect them with optical imaging techniques. These are the results that are the most original under mode 2, and actually we find out that applying poor mode 2 to a component, we were able also to clearly distinguish a kind of displacement in the Z direction that is not predicted by any of the Irwin solution or Williams solution for the in-plane solution. And what we did also, it was to extend the consideration to notch components. So actually we simply go ahead with the same approach. We add the thickness to a sharp notch components, and actually what we find out was that also Williams solution have some limitation because they don't consider, of course, the thickness effect. And if you consider the thickness effect always and again, you have the mode 2 and mode 3 are always coupled together, and you have to consider them for the design. At least if you have a material that is very sensitive to what is happening on the free surface of the component. So we studied the same case with the sharp notch. This was the finite element model. So what happens is that again we find out that there is a strong influence of the Poisson's ratio. So if you increase the Poisson's ratio, you find an increase of the intensity of the coupled mode. And again, that the coupled mode is very localized and close to the free surface of the components. Here is the mid plane. In the mid plane, actually, you don't have this effect. So you have a close effect of this component, of this induced mode that is very important, close to the free surface. We also try to give an analytical solution for this couplet mode, but in this course it's only important to know that actually the traditional fractal mechanics is based on plane models. If you extend to three-dimensional models, you have also to consider this kind of effects that are now very well studied in the literature. These papers are very recent. We published a lot of this paper from 2007 to 2015. And actually what it is very interesting is also that, of course, following the rules of linear elastic fractal mechanics, is possible to use a scale effect because we are in linear elastic hypothesis. So if you actually scale this plate in geometrical proportion, increasing or decreasing all the dimension of the plate, you can also obtain a scale dimension of the stress field, which is following the rules of linear elastic fractal mechanics for the generating mode, that was mode 2, and for the induced mode, that is a kind of out of plane mode. And so we made this kind of study for understanding if the scale effect was respect also for three-dimensional couplet modes, and in fact it was. This is the stress field along the bisector line. So actually the scale effect of mode O, if you increase the size of the component, is also increasing the stress field. If you increase the size of the components, you are decreasing the effect of the mode 2. So it's a bit difficult, but you can understand if you make a finite element model very easily. I want only to show that actually the advantage to have a linear elastic approach is that you can use overposition principle and that the scale effect is always verified. This is the most important consideration that I want to underline. Of course, summarizing, in classical theories of bidimensional fractal mechanics, we have three primary fractal modes, mode 1, mode 2, and mode 3. And of course, plane thickness is almost totally disregarded in this approach. See if the stress intensity factor is considered constant across the thickness. There is no effect in problem with stress type of boundary condition. And actually, if you consider a three-dimensional theory, you have 5 modes, 3 primary modes and 2 couplet modes. So actually the modes of fractal are not 3 but 5, because there are also 2 modes that are coupled with mode 2 and mode 3. The extension of couplet modes is strongly affected by the plate thickness. And actually there are marginal effects on primary and strong influence on couplet modes due to these effects. And also it's interesting that it's possible to predict a strong scale effect of deterministic nature considering these couplet modes. So actually, if you want to make a very accurate design, when we studied first, this approach was for a project with the aviation in Australia. And now they are implementing, because actually when you want to make light design, you are always trying to save material and you want to have an accurate design. So we developed a software based on these solutions that after that was implemented by the Australian aviation that is still using the software for design purpose, considering these three-dimensional effects. And we made this with Berto and Wang in 2005. This was, I think, the first work that I published after my master thesis. And actually, I mentioned before that Neuber and Radai were very important in notch mechanics. Actually, Radai was a student in Munich of Neuber, and they start also themselves to fight by fax on analytical solution when they were very young. So this fax is dated 1977, is the original fax of Neuber to Radai, is answering to some of the practical questions that they solved. And in this part of the lecture, I want to introduce some approaches that are useful for design purpose when you are considering notch components. I don't make much, but I want to give you some introduction to this approach. Actually, what Radai, first Neuber and after Radai made, was to try to solve the problem of a very sharp notch, so a notch with a small notch radius, averaging the stress close to the notch tip, considering a microstructural support length, which is a material property that is called rho star. But actually, so they consider that, for example, the point is not the point value of the stress concentration factor is not very important for the fatigue or fracture purpose, because as we have seen in the diagram of Frost, if you consider the stress concentration factor, you are too conservative in the design because the notch is sharp, rho is very small. And so what they try to do is to average the quantity of the stress over a material property length that is rho star. So they make the integral of the stress over this length, and the integral is called rho with a bar. But of course, if you have every time to make the integral, it takes a lot of time. So they propose a kind of equivalent fictitious notch radius to solve easily the problem. So what they consider was the real notch configuration and the fictitious configuration, which is based on a fictitious radius rho f that is defined as a function of the actual real radius of the geometry plus a contribution that is linked to the multiaxiality of the problem, S, and rho star, which is the critical length of the material. So what they did here, you have to, in this side, you have to make the integral of the stress field if you want over rho star, if you want to understand which is a critical parameter for fatigue strength purpose. On this other side, in the equivalent model, you need only to make a finite element model where you substitute the initial rho with rho f, but in this case you have a direct value which is the maximum value directly from the finite element analysis, and actually the solution is based on the hypothesis that this sigma max on the fictitious radius is exactly equal to the integral over rho star on the initial model. So it's a kind of way of bypassing the integral problem and to solve with the point method the problem of a quasi-sharp notch. Actually, the microstructural support length was discussed by Radai for different material. Actually, for steel and austenitic steel, we are in the range of 0.3, 0.4 as a critical support length of the material. And the Neuber procedure of fictitious notch rounding, of course, can be applied if you have also a sharp case, because if you have a sharp case, what you can do is simply to avoid this term that is in the initial model equal to 0, and in the fictitious notch radius approach, you have S multiply rho star. This is a method that wants actually to avoid the singular behavior, or it wants to avoid that you have to treat the singular problem of stresses that are tending to infinite close to the crack or notch tip. And actually, Radai proposed this in the standard for weldments and for welded joints. And for welded joints, the equation is rho f is equal to rho, that is the worst case condition, so rho is equal to 0. S is equal to 2, and rho star is equal to 0.4. So actually, for welded joints, for design purpose, what they are doing is to giving a fictitious notch radius that it is 1 millimeter. So if you want to design a weldment, you have to substitute the value of the real value at the weld toe with this notch radius, and you can directly read the stress field or the stress concentration factor at the point of the notch with the radius equal to 1 millimeter. And this is also reported, this is the only local approach that is accepted nowadays in the standard reinforced for welded joints. Actually, if you have a welded joints, what you can do is to substitute the critical points with the critical radius equal to 1 millimeter, and after that to understand which is the place where you have the maximum value of the stress concentration factor on that position. And you can actually design a weldment completely bypassing the effect. After that, we work a lot in this regard with radii from 2009 and later, and we apply the same concept to mode 2 loading. I have a report here for a kind of for giving you a complete overview of all these references. But actually, after a lot of exchange of faxes and a lot of fights, we develop a method that is quite general, that is able to give you actually a kind of very good approximation of the method if you try to apply it to different kind of configuration of notches, different kind of modes, and actually the papers are reporting all the solution with all the steps. The solution, the analytical solution are very complex, but what we did is at the end summarize the results in very simple graphs that are very easy to use from a numerical point of view, and very easy tables that are reporting how you have to consider the parameter S as a function of the notch opening angle. So also a person that is not very skilled with analytical tools can always use the method for designing purpose, because we are engineers at the end, for fatigue or fracture prediction. But this method actually is completely neglecting, wants actually to completely avoid the problem of stress field with many different graphs that I don't want to mention. And we also treat different kind of notches. And after that, Radai in his book is reporting directly also the stress concentration factor for the more used welded joints, in the way that you don't need also even to make the finite element models, because you have directly the stress concentration factor just made in the book, just reported in the book. So actually you can make design of everything for design purpose. And after that, Petersen, using our findings, was able to actually make some standards that, and also reporting a lot of data of welded joints, considering a lot of data and giving some design curves that are very interesting under fatigue loading, because actually they are very simple to use and based on a very simple approach. But of course, the drawback of the approach is the big scatter that you have. This means that the approach is not very accurate, so it's still something to do. So what we did, and what some people made before us, was to actually treat the singularity in some way, and so actually treat the singularity with some approach. And the first, following Neuber, the first to make this approach were Professor David Taylor from Trinity College and Professor Lucas Usman from Sheffield University. Actually, they developed the so-called theory of critical distance, and actually they were able to consider different methods, point method, line method, and area method. So actually what they did was actually to integrate the stress field along the notch bisector line and give you a kind of, in the line method you integrate along a line which is a length of 2L. In the point method you only look to the stress at a certain distance from the notch tip if it is sharp. In the case of area, you average the stress over this volume and you evaluate the stress over that volume, the average stress over that volume. I think it's also worth to mention that before Lucas Usman and Professor David Taylor, there was an eminent researcher that made the same. The first one was Peterson in 1959 that tried this approach. After that, I think this is the most relevant contribution due to Professor Tanaka, that is quite famous in Japan and is considered the king of notch in Japan. And after that, there is also a Poland professor, that is Severin, that made a Polish professor that made the same. This is an extract of a paper from 1984 of Tanaka. And actually, the idea of averaging was not first proposed by Susmel, but taking advantage of the, or Taylor, but taking advantage of the work by Neuber. Professor Shepard in 1991 proposed the idea of averaging, but she proposed to average in a very strange shape, a triangular shape that is not very significant for designing purpose, and it's also very difficult to manage from a computational point of view. She is now working in Stanford for many years, and the paper where she has reported this is dated 1991. This is the original book of Neuber, where he proposed the raw star application. This was Neuber, and this is the book in German from 1985, which is the last book that he wrote before he died in 1987. And this is the contribution by Severin. Actually, the point method, the line method, and the area method are well studied by Lucas Susmel and Taylor, that have actually made a very good work of synthesis. And I think one of the most relevant papers, if you are interested in this topic, is this one published in 2008, where they were able to apply this kind of theory of critical distance to brittle failures of polymethyl methacrylate, and considering mode 1 and mode 3, and also mixed mode 1 and 3 in combination. That was quite new at that time in 2008, and they obtained very good results in terms of predictions, with some peak in the errors, but not a big mistake. I say before that weldments are always a kind of extensive extension of sharp notch. So we have, if you consider a weldment, if you consider that usually in a weldment we have a notch opening angle of 135 degrees, and at the root we have a notch opening angle equal to 0, so we have a crack, or we have a notch opening angle that is 135. We can apply the notch stress intensity factor for design purpose, considering the stress singularity. The problem is that, as we have discussed before, we have different units of measure here and here. So usually the notch stress intensity factor is very powerful if you have failure only from the weld toe. Usually, if the weldment is well designed, we don't want internal failure. So actually, we want always to detect the initiation of cracks from the outside. We don't want that the crack is starting from the inside. So usually, if we are making a good design of the weldments, the majority of the failures are happening from this point and not from this point. So actually, what Professor Lazzarin and Tovo made in 1998 was to try to study different welded joints with different main plane thickness ranging from 6 mm to 100 mm, and the transverse plane thickness ranging from 3 to 200 mm, so a very wide range of size. If you try to summarize these results in terms of the nominal stress, you have a very huge scatter in terms of nominal stress. All the failures of these components were happening from the weld toe. If you try to summarize the results considering the notch stress intensity factor at the weld toe, you have a very, very narrow scatter band. This means that the notch stress intensity factor is a very powerful tool for designing a welded component if the failure is occurring at the weld toe. And also they extended this to aluminum components later. So actually it's not only for steel but also for aluminum welded joints. But what we tried to do later was to generalize the approach also to different kind of failures. So actually sometimes we have some components that are failing from the cracks also welded joints that are failing from the lack of penetration. So we try to get a more general approach. And so we develop a strain energy density approach, taking also actually taking in mind that the first very interesting approach was due to Griffith, but actually the first to try to make a based on energy approach was Beltrami, an Italian professor that works in 1985, and he published a work only in Italian in Istituto Lombardo of Scienze. And it's very interesting because he published 4 books on these topics that are not very well known because they were only in Italian, but that was the first trial to apply a based on energy approach. After that, of course, there are many other people that have tried this. This is the picture of Beltrami and a bit of history of him. But actually the advantage of the local strain energy dense approach is that it automatically, now I will explain a bit this approach, but the aim of this approach is mainly based on 2 considerations. The first consideration is that if you have the notch stress concentration vector, you cannot compare notch opening angle with different size. So if you have a notch opening angle of 90 degrees and a notch opening angle of 135 degrees, you cannot directly compare the values because of shifts, because they have different unit of measure. And the second point is that the notch stress intensity factor is based on the stress field close to the notch tip. This means that is a stress-based approach and not an energy-based approach. So this makes the computational efforts much more higher because you cannot use coarse mesh. You have always to use a very fine mesh close to the notch tip. And actually, what Lazzarini and Zabardi did first in 2001, and after that we extended many other applications later, was to develop a kind of parameter that is called R0. It's a reminding of the rho star value of Neuber, so it's a kind of microstructural support length that is called rho star, and here is called rho 0. But the idea is not to use a stress average in this volume, but a strain energy density instead of the stress for designing purpose. Actually, we are merging together a kind of theory of critical distance plus the consideration of a microstructural support length of Neuber. I don't want to give much more explanation, but actually the strain energy density inside the control volume is a function of the stress intensity factor of mode 1 for the notch and the stress intensity factor of mode 2 of the notch, multiply the radius r where you are averaging this quantity. So it's a very close, a very simple equation, and is connecting the strain energy density average in the control volume to the stress intensity factor that you can measure. So actually it's a more powerful tool, and the advantage is that the strain energy density has always the same unit of measure independent on the notch opening angle. So you can compare directly actually a notch with a notch opening angle of 135 degrees and the crack case, for example, without any problem. So you can consider this kind of notch and this crack, and you can always very easily compare the results. R0 is the control volume radius of the material. I will give you the definition later. And actually delta K1 is because we are thinking this equation for fatigue application, so we always use the range of the delta K. But E1 and E2 are only a function of the notch opening angle, so it's very easy to evaluate them if you have these simple expressions. So they are only a function of 2 times alpha. And this expression actually can be used using a simple calculator. And after that we extend also the same consideration to a blunt notch, not only a sharp notch. And if you consider a finite element, you can see also that the shape of the contour lines are very, very similar to the shape of the contour volume of the control volume that we have selected, actually parallel to that. So this means that the model has also some physical reasons to be very good. So we apply the same concept to mixed mode loading. So we consider the maximum tangential stress approach, so a kind of local mode 1 approach. We consider that along this bisector line we have mainly mode 1 loading. So what we did was simply rotate the volume under poor mode 1 to a volume like this, maintaining the length R0 for both the volumes. Is simply rotation of the volume. So the method can be applied also to mixed mode conditions. And we define the control value of the radius R0 as a function. So for defining the control radius under static loading, you need two fundamental parameters. You need the energy of the material for the unnotched material, and you need the energy of the material for the crack material. So you need the test from the unnotched specimen and the test for the crack specimen. If we consider as a critical parameter the energy for the material, what we actually have is that we have to consider that the energy for failing the unnotched material is the same energy that we use for failing a crack material. If you equate these two equations, it's possible to obtain R0, which is a function of the Poisson's ratio, is a function of the fracture toughness, is a function of the ultimate strength of the material. So actually, is a very simple closed form expression that is giving you R0, that is a material properties, as a function of some simple test that you can easily make on standard material and also complex materials. We try to apply the approach to different configuration of notches, and as a function of the notch radius. Was made in collaboration with Professor Elises and Professor Gomez in Madrid. At the end, we were able to make a synthesis of more than 1,000 results made from us and taken from the literature, about 900 results, where actually the critical radius was ranging from 0.4 micrometer to 500 micrometer. Actually the ultimate strength of the material was ranging from 2.5 to 1,200 megapascals, so from a kind of very soft polymer to almost a ultra strong steel, with a fracture toughness ranging from 0.15 to 55 megapascal multiplied square root of meters. So a large variation. Mode 1 and mixed mode load were included in this cutter. So the results were quite good. And also we applied this to graphite under mode 1 and mode 3 loading. Actually, this was the first time that we applied the strain energy density criterion also to mode 3 loading. And of course, we also applied the same consideration. First, to the data that Lazarin and Tovo obtained in 1998. We defined for the weldments with the same consideration that we made before for static loading. We actually consider a welded material without any geometrical discontinuity, and this is the critical radius. So the energy of this component has to be equal to the energy close to the notch tip for this component. So the energy of the unnotched component has to be equal to the energy of the notch component for determining the value of the critical radius. So you need always two information. In this case, we were thinking to fatigue, so we were referring to the critical value of the notch stress intensity factor at 5 million cycles, for example, and delta sigma A is the value of the unnotched material at the same level of number of cycles. In the literature, you can find that these two numbers are this one. This is the value of the critical value for the unnotched material, unnotched weld material, and this is the value of the critical stress intensity factor, critical notch stress intensity factor for welded joints. Actually, considering failure from occurring from the weld toe and weld root, we were able to summarize more than 900 fatigue data for weldments in a single scatter curve that can be now used for design purpose, at least for steel, if you consider a critical radius of 0.28 millimeter. So, which is the advantage of the approach is that you can use very coarse mesh. So you don't need a very refined mesh for making any calculation. But actually, if you consider, this is only a plane case, so a bidimensional case, but if you consider 35 elements in the entire model and 5 elements in the volume close to the notch tip, you can actually evaluate the strain energy density very accurately. If you consider the notch stress intensity factor, if you want an accurate value of the notch stress intensity factor, you need a very fine mesh like this close to the notch tip, which is very, very heavy if you consider three-dimensional models. So we actually give some guidelines in a paper published in 2007 and also in a paper published in 2010 in how it has to be made, the mesh close to the crack tip to make efficient the method. And after that we apply to different configuration. What it was find out is that considering a fine mesh, you have this value of the notch stress intensity factor. And considering a coarse mesh, a posteriori you can derive the notch stress intensity factor, deriving the stress intensity factor from the strain energy density. And the mistake that you have, or the difference that you have, is very small, so it's almost 3–4% in terms of notch stress intensity factor if you use a very coarse mesh with respect to a fine mesh. So this is very efficient. Of course, this method is very powerful if you use it for a three-dimensional component. You can use a very fine mesh like this close to the notch tip, and you can evaluate the three-dimensional the energy density in a three-dimensional model very easily with a very light model. So we compare, for example, mesh 1, mesh 2, mesh 3, mesh 4, mesh 5 with different increase of the size of the volume of the elements. We reach the extreme case of 4 elements in the critical radius are 0. And if you compare the results, if you put more than 1,000 elements inside the volume and 4 elements, you have a difference that is 2%. So it's a very efficient method. Actually, we use the method for designing the Panama Gate. So in 2015, we start this project in collaboration with Simolai, that is a big industry in Italy making large civil construction. And also the transportation was made by sea. What we did was to actually we were able to actually the Panama Gate was composed by 8 of these gates, and every gate has 50,000 weldments plus 1.3 million of notches. So, and these gates are subject to fatigue because also the transportation was made from Europe to the Panama Gate using this ship with waves in the sea of 10 meters that were cyclic loading to consider in the design. Okay. And we developed a very interesting tool that is based on artificial intelligence and neural network that is able, and machine learning, that is able actually to design in an efficient way. It is also able to remember previous details that were just considered in the design without repeating any finite element, not useful simulation if the details of the weldment was considered before in the computation. It was the first time that we applied this. If actually when we started the project, there were almost 30 engineers that were dedicated to the design of the gates. And what they did was to design every single nodes, critical nodes, one by one. But with this automatized model, we were able actually first to make a macro model of the gate to detect the most critical point of the gates, and after concentrate our attention only on the critical nodes of the structure and not to all of them, because sometimes many of them are without any load. And this is other application for ships. We work together with Hamburg University, where they have a very strong history for ship design, and we apply to the energy approach to these kind of details that are quite strange. with a very good success, because the master curve that I have shown before is the red lines, and all the data for three-dimensional model are exactly falling inside the scatter band. So the master curve is respect also for these kind of details that are quite complex. Actually, if you want to understand or to read more about this, there is a recent works by Professor Dieter Radai and Michael Worman that is called Advanced Methods of Fatigue Assessments, that is reporting all the basics of notch mechanics, and is also reporting a lot of the consideration that I made today regarding the approach. Actually, we support Radai right in the book. We are mentioning in the introduction, but after that it's always useful that other people are saying that what you are proposing is good, because if I'm saying that I'm proposing something good, I'm not trustable because it is my approach. But if the German school start to believe that this method is useful, I think that is probably useful. And actually, we also summarize in a recent paper. This was the best paper that I wrote with Professor Lazzarin in this journal with impact factor. I think you are familiar with impact factor now. This journal is an invitation. They make invitation only to special authors, and when we publish in the journal, it got an impact factor of 30 almost. So it was a very high impact factor, and actually they dedicate a complete issue to a paper. So we made a 50-60 page journal paper, and the issue was also reporting in the cover our tests, so it was quite nice. And also they paid me, I think, 600 euro per page or something like this, or probably less, but no, I think 600 euro to all the, but I also received a kind of honorarium for writing the papers, which was the first time in my life. And I wanted to close this lecture with, because actually what we are considering is in fractal mechanics are mainly defects, cracks, and notches. But this is very relevant if you consider additive manufacturing, because nowadays I think more of us are speaking about additive manufacturing and three-dimensional components, 3D printing, both in polymers or in metallic material, steel, Inconel, or titanium alloys, so we can print different kinds of components. And what it is very interesting is that all the tools that we have seen before, and all the analytical solution that we have seen, and all the approach, including the strain energy density, can be adapted to the additive manufacturing design in a very smart way, in a very quick way. So we don't need to reinvent the wheel, but we can really use some of the previous concepts that we have developed. Of course, what it is critical for additive is that sometimes you have a notch, and close to the notch you have a defect that is induced by the process. In that case, the problem becomes more complex. But I think it's possible to treat it, because the overposition principle is possible if you don't have a large plasticity. And if you are working especially at high cycle fatigue, the plasticity is not so big. So what we did is to start to play a bit with the topic. We made different kind of notch configuration, a notch specimen, semicircular notch, a V-notch with the notch radius of 1 millimeter, a V-notch with a 0.1 millimeter, and also we plot the fatigue curves showing the size of the defects that we find in the component. So we are not only plotting the stress level, but also for each shape of for each Euler curve, we are also reporting almost the size of the defect that we find in the component. I think is a nice representation. And we try to propose a kind of diagram to understand for no-notch, blunt notch, sharp notch, and crack, what is happening in terms of failure, in terms of mechanism. And after that, we also try to apply the strain energy density. We consider only mode 1 at the moment because the topic is quite new, but actually the results are very promising, and it is very evident that the strain energy density, if used properly, can be a very good tool also for predicting the failure of under fatigue loading, at least under linear elastic condition for these materials. Of course, this is an engineering approach. I don't want, if you want to study the mechanism of failure, to understand the physics behind this, it's a very complex tool. If you want to design and give to an engineer, which is the stress level that you can have at a certain number of cycles. You have to accept an intrinsic scatter, and I think it is what we can do as engineers. So I'm an engineer, I'm not a physicist or a mathematician. I want to have at the end something for some tool for designing purpose. And we also change different materials, so we are working on titanium. Of course, the process is affecting a lot of the surface roughness, and what it is also important to consider is the residual stress effect that you have close to the surface for these components, for these materials. But I think with post-treatment that can be mechanical or HIP, so hydrostatic pressing, you can actually reduce the level of porosity, and you can also making post-treatment for releasing the stress, the residual stress, so you can actually apply very easily concept that we have developed before. I want to close this lecture. I was actually quite lucky and proud of my career, because I was so lucky to meet a lot of interesting persons in my life. Actually, first I want to thank Professor Lazzarini. I worked for him and with him for 15 years, starting from a course that he taught to me in 2001, and after that we worked together until he died in 2014. This is Professor Murakami. We made this picture in Trondheim when we went to the European Conference on Fracture in 2014. This is Professor Adai. I met him in Vicenza when we invited him in 2011. This is Professor C. I organized with him several conferences on mesomechanics. This is Professor Tanaka. This is John Hutchinson. This is Paul Paris in this hotel in 2014. This is Jim Rice. So this is Ali Fatemi. This is Leslie Banks. This is Yoshi Ong. This is Ali Fatemi, is very famous for multi-axial fatigue. This is Professor Lazzarini, me, and Professor C and Professor Risitano in Vicenza, in my own city. And so I think, as I said before, this lecture is not only for teaching you something. I think probably I was very quick, but at least you have a lot of materials, and I think if you want, you are welcome in Norway for collaboration. Some of you guys have just visited me, so I'm quite happy about this. Some of the disadvantages of Norway is that this is the summer time, so it's not very good, but the advantage is the typical Norwegian family for male. For par condicio, I have also put this for girls, because we have a very good gender balance. And so this is the end of my presentation, and thanks a lot for your kind attention. I made a long presentation, but I hope it was useful. I think tomorrow you will be more focused. We will be more focused on different topics. Okay, thank you so much.